All right, well, thank you very much. Thanks again to the SOC for the opportunity to present our work that we have accomplished over the past year within Resource. And just to give you a background on what Resource is, so we're thinking about going back to the moon. So you want to figure out robotic and human missions, or we want to support them in the way that they can be sustainable and affordable through the survey target bodies. So one of the key things is that we want to know where the resources are in terms of their location, how much is there, how are they actually distributed, and how can we get them out of the ground. And for that, we are developing missions hardware with ISRU, prospecting, the excavation of it, the transportation from the location to a facility, and processing steps to support the whole endeavor. There you go. So there's really 3 tasks within the research project, which is doing the science, which is assessing and characterizing the resource inventory of survey target bodies. And then task 2 is the ISRU technology development and the testing. So it's really about the hardware. And then third is assessing the concepts of operations, the capabilities related to human robotic interactions in support of lunar robotic ISRU. So this is really kind of like the operations of how do we actually do this. So to summarize some of the work we've done, finally last year in the summer, in the previous years, we had to postpone our field campaign, but it finally happened in last year. And our field site was the Galena Rock Glacier in Wyoming, and we can see there's an array of teams that went out to do really cool geophysical work. And the objectives were to test geophysical techniques for detection of subsurface ice on planetary bodies. And for that, we had technology testing and TL advancement of lunar subsurface access systems, and specific, we're talking about a drill development here. And also, how do we go forward with this? How do we implement this? How do we operate such a activity with in mind to do this in space, related to the mapping, the sampling, and the drilling systems, and also the geostatistical assessment of the geophysical data collection and the requirements for developing predictive capabilities to know where it is actually in the ground, that we have an idea about where to go. So that will be a summary in here. And you see one of our friends at the USGS, which is also in the room, Colin Walters, where they have been deploying geodes all over this lovely field site, which looks terrifying to walk on. I haven't been there, but I'm sure our people had a lovely time. That's really what it is. It's a rock glacier. So, and on that satellite image, you can see where things were deployed along the top of the rock glacier. And what should I say? So some of the results that you can see are, or should say that we have the rock is basically overburdened, and underneath we have ice. So there's an interface in here, and this is what we're trying to be detecting with these techniques and mapping it out. We'll go back to this, but one thing to say on why we're doing this is important, because this is actually going, the technology like that will actually be flying to the moon in 2026 to actually put out geodes on the surface on the moon to measure, passively measure the seismicity on the moon for about 14 days on that mission over here through Eclipse delivery. So that's why we're doing this. And some of the other work that what we did is actually drone-based GPR mapping. And if you're looking at this, I'm not a geophysicist, so I can explain this on the most basic level that I can. But what we see is that when we're using this technique, we can actually find reflectors in the ground that tell us there's a change, and that's where we would expect ice to be. And over here, you see that again, the rock glacier, and it's actually tracing out where the drone's been flying and how we kind of like what density we mapped and what areas we mapped out to come up with such a kind of like underground view of that glacier. And over here is comparison between two different time steps, essentially, and a little bit of a different technique, but we can all see structure in the underground along this glacier using that technique. So what we then wanted to do is actually look what we see, how does that correlate with the ice essentially. So we have our friends at Honeybee Robotics that came out and they brought a drill essentially. So what they've been doing is first kind of dug a hole and then tested the technology, the drill in this field site to actually hit the ice and drill into it. And that's what we accomplished. So what do you say? I think in a nutshell, that's what we have done, and we could find the ice. Of course, we want to be responsible in the field. We're on a glacier with ice. We don't want to disturb anything there. So what was done after we were done is actually fill up the hole. We did put some thermal probes in there to measure over time the thermal environment, but we want to be really not intrusive into the natural environment in these field sites to actually cover this back up to leave the site undisturbed. Here. So more about the drill development that Resource is supporting, again, with Honeybee Robotics, is to actually develop a drill that can drill like 10+ meters down. So if you know about Viper rover, 1 meter drill that is developed, but you might want to go deeper. And one of these drill capabilities that we are supporting is called Rebels. It's the rapidly excavated borehole for exploring lunar subsurface. And it's essentially a drum of drill strings that can be lowered into a drill hole. And we can see this kind of sketched over here. The really cool part, thank you, is that we're actually bringing instruments into the ground instead of excavating things to the surface and making measurements there, is to bring instruments down into the ground, down the borehole instead, and make the measurements on the spot. Also, when we're thinking about getting like these ices out of the ground, what do we do with them? They're probably impure. If you want to do fuel grade hydrogen and oxygen, you probably want to get rid of these impurities. And our colleagues at JSC, Aaron Paz, is leading the development of a purification facility and how to extract all the impurities out of the icy or the water to use it then or refine it into fuel grade components and that hydrogen and oxygen. Thinking about sending things to the moon, what we have also developed in terms of the heart rate is actually a commercial available Kinect camera. Some of you might know Microsoft Kinect cameras that we have actually taken apart and ruggedized it to go into space, and it will actually fly to the moon with the Lunar Outpost CLIPS mission soon. So that is in development, and one of the ways we tested this technology is actually taking it out to the Survey lunar testbed to use that camera and take images. And this is what you see with that camera. So it's a really nice high resolution camera that sits on a really small rover that can explore the lunar surface. So we'll test that flight capability once it's in space flight, that it actually can work in space as well. And from that, we can generate 3D maps or 3D scenes of the lunar surface to do all kinds of other work with. So it's not just an imager, it's actually providing you the depth data for the scene you're looking at.
1 minute.
1 minute, okay. And then lastly, one more of the science part is that we've, one of our colleagues, Ariel Deutsch at NASA Ames, has published a study on surface darkening, and this was based on a study for mercury, where we can see that things change depending on the temperature that things nanophase iron is annealing at higher temperatures, and that might have to do, that might contribute to surface darkening. And this is mercury, so it is probably likely that this kind of process that is outlined in that paper is happening on other bodies as well. 20 seconds or so, and I'm going to finish up with that one slide that we're also really committed to STEM engagement through Resource. We have an awesome team at Howard University in APL that's developing wonderful science workshops with teachers and STEM workshops where teachers are really highly committed to implementing that concept that has been developed into their own classrooms to teach students. I'll end it here just because we're out of time, but if you have any questions, I guess will be happening in the Q&A. Thank you.